Hey folks, and welcome again to Advent of Code in F Sharp. This is day 9 already, and actually it's the 10th of December because day 9 took me a while to solve or to find the time for it to solve. And it was a bit of a tricky problem, so this won't be a live coding session for day 9, this will be a recap of what I did in a couple of hours. So maybe a quick reminder, day 9 is the rope thing, where you have a rope that is moving given some commands, or the head of the rope is moving given commands like this, like right 4 steps, left 5 steps, stuff like that. And then the tail follows along like in the video game Snake. And there's some shenanigans with diagonal jumps, stuff like that. Part 1 was doable, except maybe for the tail jumps. It took me a while, and I was trying to be smarter than it had to be. I just, in the end, went for a literal one-to-one translation of all the examples and all the cases to steps. I'm sure there are more elegant algorithms out there, but I'm not here for the elegance. I'm here to grab some stars or some star fruit, and we did. So, let's skip to part 2. Where things get more interesting, because instead of one single tail, we have a rope with 10 knots, and every knot acts like a tail for the preceding or for the previous knot. So it was like a 10-fold increase in complexity, or in the number of steps that our rope had to jump around. It was a pretty interesting problem. The example itself was pretty big, so yeah, let's drop into the code. If you need more information, you can find it on the Advent of Code website for day 9. So where do we start? Let's start at the types, or let's start with the types. I declare my 2D locations as a tuples of ints. My rope, for part 2 at least, is a list of locations, where every location is a location of a knot, one of those 10. Then you have those 4 motions, and an instruction is one of the motions, and a distance. Then we have some parsing. Again, I'm going to fold, so I declare some state. So let's maybe now drop to the outer function, or the main method for today, so we can begin. The parsing was pretty straightforward. It's just parsing instructions, and then, as always, if we have a list of instructions and we want to get run every instruction and maintain state in between, that's a fold for me. So again, we use the fold here with some function called apply, and apply applies a single instruction. So for example, left 5 to the current state. But because left 5 is actually 5 steps to the left, I had this other function, apply recursive, that takes one of those 5 steps. So it's literally recursion, so if we have a distance of 0, then we're done and we stop working, and otherwise we take one single step with this move 1 function, and we descend recursively with a smaller distance. Next up is this move 1 thing. That's literally just saying, let's move the head, and then let's move all the next knots. That's because the head follows the instruction, so that's the left 1, left or right 1 kind of thing. And the tail follows the head, so it's a bit of a different behavior. That's why I decided to split these up. Let's take a look at move head first. Move head is pretty straightforward. Given an up, we move our y coordinate, and so on and so on. And we leave the tails untouched. And then we have move tail. That takes a look at everything except the head. Or it takes a look at the head, but it takes a look at the heads because we need the preceding or the previous knot. And again, you'll see here a fold. So for every knot in there, so for every knot that is not a head, we do something. And what we do is we do something called move knots, given some kind of state. And the state is all the knots we visited. And for the first non-head node, that's the head. So move knots just takes a look at the last knot we've seen and calculates the new location for the current knot and appends that to the list. And in the end, we can just reverse that list, and we're there, and keep track of every location that the final knot in the rope visited, because that's what we need for the answer. And then this is the new not location function. That's just a bit of calculations. And this is where I got stuck while doing the live stream. I was trying to be too clever. I was trying to figure out the one-liner or the two-liner. And I'm sure there is one. I have not taken the time to go look around on the interwebs. But I ended up on a 1, 2, 3, 4, 5, 6, 7-liner. Close enough. That's just some coordinate magic. So if we were, for example, on the same row, no, if we're on the same column and we're 2 rows apart, then we can inch our inner knot 1 step closer, stuff like that. And this is the somewhat trickier diagonal jump when we're really far away or when we're not touching in diagonal. So yeah, it was a fun little problem. My lesson learned is do not think you are more clever than just following the examples first. Maybe I'll try building up from a literal implementation and improving on that instead of the other way around. Pretty sweet. Exercise. It's, I think, the first one where I actually had value out of writing some tests. So that's exactly what I did for all those special new location calculations. Yeah, really had fun, but nothing new here, just folding, some domain modeling. We've all seen this before. So this was a summary for day 9, and I'll see you again for tomorrow's puzzle. Bye bye.